Alright, so starting today we will try to talk about second order differential equations. And starting from second order and higher, the equations become pretty tough. So we will limit our discussion to linear differential equations. And later on, you might have a chance to work with some nonlinear differential equations in your other engineering courses. But still, knowing how to deal with linear ones will help you deal with nonlinear ones too. But they're kind of really different. Once your equations are not nonlinear, it becomes really hard. Now, I'm gonna take a totally different approach. So I first want to talk about the three properties that mathematicians ask when they first see any differential equation. The first question is existence. Basically, you ask, is there a solution to this differential equation? Even if you don't know whether the solution exists, what exactly the solution is, can you at least verify that there is some kind of solution? Is there a solution? Second question is uniqueness. And by the way, when it comes to existence, there's a theorem by Pickard that shows you that any linear differential equation will have a solution for a little bit. There's some technical conditions that has to satisfy, but you can just roughly can say if it's a linear differential equation, you always know that there's a solution, okay? As long as the coefficients are not crazy. Okay? All right. The second question is uniqueness. The question is the solution unique? And the third question people ask is stability. In other words, does the answer change rapidly due to change in initial conditions? Now the third one is only of interest if this is a differential equation that has that can only be solved numerically. I told you that there are some differential equations where you can't write down the solution explicitly. You can only talk about its numerical solution, approximate solution. But if you're talking about approximate solution, then the question becomes, what if the solution varies really a lot if you have just minor difference in the calculation? Then the error might be so huge that your calculations, your approximations may not be believable, may not be good enough. So this is only useful for people who are doing numerical work, because in this class we're not doing any numerical solutions. This third question won't be any importance. It won't be any importance to us. Now, when it comes to nonlinear equations, these are very hard to answer. We don't know if the given equation has a solution, or it may have more than one solution. stability is an issue. For example, differential equations that govern the weather is nonlinear, and it's highly unstable. That's why you have this thing called the butterfly effect. If a butterfly flaps in Beijing, then there's a storm across North America in 2 weeks or something. So those are all from lack of stability. If you have an equation which is lacking stability, then you may be able to have a good enough solution for a small value, but then when you're trying to forecast for a long time, then it will be hard. Okay. All right. So this we don't care about. Let's talk about these two, existence and uniqueness. What does it mean? Oh. Let's go back to, say, junior high, 7th grade, when you were first taught algebra. And let's say you have 3x plus 9 equals to 15. Now, the algebra teacher will say you have to move the 9, you have to subtract 9 from both sides, divide by 3, and get 2, right? So you have to do all this algebra to get the answer. But some smarter kids will just look at this equation and say, I think 2 is the answer, right? And they will just write x equals to 2 without any calculation. And then the algebra teacher will take points off because he's not doing it the proper way, right? Now, the way we are going to solve second-order differential equation will be exactly like this. So rather than trying to go through all the intermediate steps to get the answer, we're just going to say, it's of this type, so the answer must be something like this. So that's the answer. Yeah. So basically, we'll be guessing the solution rather than solving. Of course, there will be some more to it rather than just guessing. But what we're going to basically do is, given a differential equation, I'll say, what's the solution? I'll just make a guess, and I know that's the solution. And then you try it, and if it works, it works. Okay. Now. That's a totally new way of doing math, because all your life you're taught that that way of approach is wrong. Well, how do mathematicians justify? Well, this is the way they justify it. Because solving differential equation is such a long and tedious work, what they did was they changed their game and said, well, I'll do this. For linear equations, I'll prove that the solution exists, and I'll also prove that the solution is unique. And once you have that, and then, so let's suppose that here's the equation where we know that the solution exists and it's unique. Okay? Now, existence of solutions justifies that you can guess, right? You can make guesses and try, okay? And I tried too, and it did give me a solution. Then the uniqueness tells me, well, I got the solution and there's only one solution and I found it here, so that's the answer. So these two theories, existence and uniqueness of differential equations, we'll be able to justify our guesses if we do come up with an answer. Does that make sense? Okay. So it's like this. In terms of differential equations, here's an equation: y prime equals to y, and then y of 0 is equal to 1. Now this is a first-order linear equation. So I know that the solution exists, and I know that the solution is unique if you provide one initial condition. See, you know that if you solve this, you get C, and to figure out the value of C, you need an initial condition, right? So the statement of the uniqueness theorem goes like this. If you have a first-order differential equation, and you have one information about the initial condition, then there's a unique solution. That's how it goes. So let's say you're given this. Now, until now, we were kind of trying various methods of solving, right? But from now on, it will be like this. Y equals to e to the x satisfies this. And if you plug in 0 for x, y becomes 1, so this satisfies both, right? So I know that that's the solution to this, and because of the existence of uniqueness, I know that this is the only solution. Done. Yes?
Wait, but if you're saying that y is equal to 0 and you're putting 0 into x, how does that make sense?
No, y of 0 equal to 1 means x is 0 and y is 1.
Oh, okay, I got you.
Yeah, then when x is 0, y is 1. Okay? So when x is 0, either 0 is 1, so it does work. So this satisfies both, so it's good. So that's how our approach will be. Okay. So let me show you a little more serious example. This is this first order. I mean, if that's the only thing that you do, then basically I'm asking you to memorize all the possible answers. But that's also not the ideal way, right? So it works like this. For the simplest case, when you have y double prime minus 3y prime plus 2y equal to 0, okay, let's say you're given this differential equation. It's the second order differential equation whose coefficients are zeros, constants, right? Now, and then also the right side is 0. In this case, you call this, if this is 0, you say this equation is homogeneous. You call it homogeneous. Constant coefficient, homogeneous, second order linear differential equation. That's what this is. And you will learn, well actually I'll just tell you now. If you have a homogeneous, constant coefficient, linear second order differential equation, then the solution always looks like the following. Y equals to e to the rx. I mean, one of the solutions will always look like the following. And then if I know this, then what can you do? You can just plug that in and figure out the value of r. Right? So it's like semi-guessing. So it's an educated guess. So it's like a trade-off between just guessing out of the dark, like shine in the dark, and having to actually solve this. You can actually solve this using some more elaborate methods. But that takes a long time. So this is like the middle ground. It's not like completely guessing. It's not completely solving, but it's some educated guessing. So I plug this in here. So let's see. How do you plug this in? First, y prime is, what's the derivative? R times e to the rx, right? What's the second derivative? R squared e to the rx, right? If you differentiate, every time you differentiate because of the chain rule, r comes in front because see here r is a constant, okay? Plug it in here, we get r squared e to the rx minus 3r e to the rx plus 2r e to the rx. No, it's not. 2 e to the rx equal to 0. Okay. See how I replace y double prime by this, y prime by this, y by this? I took this and did this change of variable. I plugged these in and this is what I got. Okay. Now I can factor out the e to the rx because that's the common factor. What's left in here?
R squared minus 3r plus 2.
Now, can exponential functions be 0? No, exponential functions can never be 0. So the only way this could happen is when this is 0. So let's see, r squared minus 3r plus 2 is 0. And then you have r minus 2, r minus 1. So you get r equals to 2, r equals to 1. That means not only we have one solution, we actually got two solutions. So we got y equals to e to 2x, that's when r is 2. And also y equals to e to the, 2x. E to the x, that's the other solution. Okay, so we got two solutions. And now let's think about what uniqueness means in this context. This is a second order differential equation that means the uniqueness theorem for such is given like follows. If you're given two initial conditions, so if you're given the value of y0 equal to something and y prime of 0 equal to something, if those two values are given, then the solution is unique. Okay? Now, what does that mean? That means these equations have how many undetermined free variables? Like C? What do you think?
3.
It will have two, C1 and C2. It will have C1 and C2. Because each information will give you an equation for C1, the constants. So if you have two equations, that means you must have two non-determined values. Okay, so there are two free variables if you are trying to solve this. Okay, so here's what we have. We have two solutions, and we also know that if we want the final solution, it must have C1 and C2 somewhere. Okay, and then what you do is after you find these solutions, you take something called the linear combinations. C1 e to the 2x plus C2 e to the 1x. You take C1 times the first function, C2 times the second function, and you set that as y. Then we know that this is all the solution of this. Okay. Now let's see why. Now, first thing you can do is you can actually differentiate this twice and plug it into the left side and see it does satisfy this equation. You can check. Do you want to check? Or you don't have to? Okay, let's check. Let's see why that's the solution. All right, y equals to C1 e to the 2x plus C2 e to the x. Y prime is 2C1 e to the 2x plus C2 e to the x. Y double prime is 4C1 e to the 2x plus C2 e to the x. And then if you multiply -3, this will be -6. There will be -3. Okay, and if you multiply by 2, and now add. Let's add. On the left side, you get y double prime minus 3y prime plus 2y. And over here, what's 2 minus 6 plus 4?
0.
0. What's 2 minus 3 plus 1?
0.
Oh, so I know that the original thing satisfies the equation. See? When I plug this thing in to the equation, I get 0. Yes? So we know, we did verify it's a solution. Okay, well.
Professor?
Yes, yes.
Why do you multiply by 2 and -3?
Okay. I don't think you're really understanding what I'm doing here. Let's do it again. Okay, so we all agree with this? If I set y as this, these are the first and second derivative? Is that good? Okay. Now then, let's try to compute the left. Let's see what happens if I plug this into the left side. If I plug this in here, what do I get? I get this. Is that right? Okay. So I'm going to get, instead of y double prime, I'm going to get 4c1 e to the 2x plus c2 e to the x. And then if I plug this into here, that's I have to differentiate once, and I have the derivative here, right? So it'll be -3, 2c1 e to the 2x plus c2 e to the x. And then if I plug in this to here, it will be twice of c1 e to the 2x plus c2 e to the x. Okay, now let's see what happens to e to the 2x. It's 4c1 e to the 2x minus 6c1 e to the 2x plus 2c1 e to the 2x. And then what about e to the x? It's plus c2 e to the x minus 3 c2 e to the x plus 2 c2 e to the x. 4 minus 6 plus 2 is?
0.
1 minus 3 plus 2 is?
0.
So what did you get? You got 0. Okay? Convinced now? So you do see that this is a solution to this differential equation. Is that good? All right. So here's what we observe. Once we make guesses and find two individual solutions, then for any linear homogeneous differential equation, taking the linear combinations of the two functions gives you a solution. That we can agree. We just verified it's a solution, right? Yeah. And not only that, it has two free variables, which will be determined once I give two initial conditions, right? So that means this is the general solution. Okay? This is the most general that you can have. So that's it. The uniqueness says that this is the solution. And we didn't really have to get our hands dirty. We didn't really try to solve this. Rather, what we did was we looked at this. We looked at that differential equation and made guesses and took the linear combination, and that was it. You don't even have to go through this step. You can once you have this, you take the linear combination. That's it. Then existence and uniqueness tells us that that's the solution. That's all you have to do. All right. Now, maybe I should show you how you can actually solve this, and then probably you're more convinced that this method is less suffering. Okay. So how would you actually solve this? So here's how you solve it. So if you're given this, you can say this. You can do y double prime minus 2y prime minus y prime minus 2y equal to 0. Are these the same? Yes? Right. Minus 2y prime minus y prime, same as that, right?
Yeah.
And to figure out why you would want this, that takes another new way of thinking. I'll just show you how it's done. Okay, so we did this, so we agree that this is true. And then I can say this is y prime minus 2y prime minus y prime minus 2y. Okay? If I differentiate this, you get the same thing. Okay? So this is same as that, that's same as that. So we're still solving the same equation. Then I'm going to change a variable and say z is equal to y prime minus 2y. So that this differential equation is now z prime minus z equal to 0. Oh, I know this equation. What's the solution? Z must be? Hmm?
0.
No, what function?
1/2 c squared. E to the x.
E to the x, yeah, e to the x. E to the x is the function whose derivative is same as itself. Isn't that true? Okay. So I'm going to put a c to this. Okay. I mean, of course, to really justify this step, you should treat this as a separable equation. You divide by z and multiply by dx, and you integrate both sides. That's how you get. But we've done this before, so it's not like totally new, right? You know that the solution of this is that, okay? All right, but what was z? Z was y prime minus 2y. So this is what we have. We have y prime minus 2y equals to c times e to the x. And finding z is not enough. We have to find out what y is, right? So how do we solve this? This is a first order linear equation, right? So what do? You use the multiplier. E to the integral of -2 dx. So e to the -2x. That's the multiplier. I multiply this both sides. Just like that. Okay. And then this is a product rule. I mean, that's the purpose of the multiplier, right? Multiplier turns the entire left side into a product rule. C times e to the -x. And then you integrate both sides. And then this becomes e to the -2xy. And that becomes negative c e to the -x plus c prime e to the, just c prime. Right? So if you integrate e to the -x, it's negative e to the -x, right? And then this is c prime. And then finally, you multiply e to the 2x both sides, and you get y equals to negative c e to the -x times e to the 2x plus c prime e to the 2x. So I'm multiplying e to the 2x both sides because e to the 2x times e to the -2x, they cancel each other. You know that? Right? They cancel each other. Yes? No? Yes? Okay. Give me a nod or something, or I get really nervous and I explain the same thing over. Okay, then let's see. What is this? This is e to the positive x. Negative x plus 2x is positive x. Plus c prime e to the 2x. And if you compare this to our original solution, it's the same thing. The only thing is that we call this as c1, and we call this negative c as c2. That is the same exact solution. Do you agree? Right? It's the same exact solution, right? Yeah. So, I mean, trying to solve a second order differential equation this way is doubly long because, I mean, it's a second order differential equation. You have to solve it in a series of two first order differential equations. Just like if you're trying to do two integrals, you have to do one integral and another integral. It's something like that. Okay, and that's why at this point it's no longer feasible to actually go through all the calculations for all kinds of equations like this. So rather than having the viewpoint of solving this differential equation, we're going to change our perspective and say, oh no, we're just going to make guesses, but some educated guess. Okay, we're going to make educated guesses, and then if it satisfies, then the mathematicians kindly gave us these two theorems, existence and uniqueness. So we're happily just using that theorem, so we're good to go. Okay, so really, you have to thank the mathematicians. If they didn't prove that existence and uniqueness, then all this work is not justified, and you may end up thinking, well, I have this solution, but is that all the solution I have? Maybe not. There's always this this bad feeling about what you're doing. Yeah. But now, because of those theorems, you have some peace of mind, even if you really didn't solve it, you're just making guesses.